lab this week? Last week we had lab this week. On the syllabus it says no lab this week.
No, that's not what it says. First of all, hello, I'm glad you're here. There are labs this week. The syllabus says there is a lab. The current syllabus says. Yeah, syllabus changes like weather. So there is lab. There is. However, that lab takes place in a different room. Not the usual 134, but the next one, 136. So, as you know, this lecture is optional. You don't have to press anything. This is mostly just for fun and for you to compare what you think with what other people think. So, what's going to happen? You've seen this before, and this object has a certain moment of inertia. And the question is, what will happen to the moment of inertia if we move these two weights closer to each other, to the middle, like this? So choose your answer. Remember it, because I'm going to switch to a camera. Because there's also demonstration directly related to this situation. Two weights, and the location of those weights affects the mass distribution. The mass distribution affects that physical quantity I. We call it moment of inertia. And that affects dynamics of the system. So, okay. This is a physical equivalent of the setup for your upcoming lab. A weight attached to a pulley, well, cylinder, and if we let it go, the whole system starts moving. Starts moving. So the weight travels down, this thing spins, and why is it so slowly happening? Well, the inertia is high. So how can I change the inertia? Well, two options we can use. We can change the mass, so make it lighter. For example, just taking off these two heavy weights. But I don't want to change the mass. That would be too easy. All I want to do is change the mass distribution. So I'm going to move these two weights closer to the axis of rotation. And we have only three possible situations. Number one, nothing changes. Number two, inertia increases. Number three, inertia decreases. If inertia goes up, it should move even slower. More inertia, harder spin. But if the inertia goes down, so clearly it affects it and moves. Now the acceleration in this situation is different. If it's been faster and faster and faster with a faster acceleration, higher acceleration, that means the rotational inertia of this system now is, what do we say, greater, less, equal to the original one? Greater, original, the new one. The new one, same, greater, less than original. What do you say? Case number one, case number two. The inertia for case number two Less, of course, less inertia, because we can see that in the second case, when the same weight was attached to it, it was accelerating at a faster rate. And in this situation, again, we can try just rotate it using my hand, your hand, and you can feel how hard it is. But if you move it closer, it's much easier now to rotate them, because rotational inertia is down. So the answer, and maybe one more, the answer to this question is decreases. All those equations which we see on the screen tell us that if we don't change this variable, this parameter, we don't change the mass. We change mass distribution. So we make it closer. If this parameter goes down, the whole product goes down. And a similar question we could have asked about the motion. So two objects. These two cylinders, a hollow one, a solid one, we've seen it before, they have the same mass, about 400 grams. So what's different? Mass distribution. So we kind of pulled away the mass inside this closer to the edges, to the rim. So this is getting denser and denser. So this hollow disk should have more inertia than this one. For the ring, the coefficient equals 1, and for the solid cylinder, the coefficient equals 1/2. Everything is in this coefficient. You see, for all these equations, for all of them, the structure is the same: mass, some distance squared, usually the radius, and only the coefficient is different. And here, sphere, cylinder, the sphere here has the coefficient, we call it form factor 2/5, cylinder 1/2. Which number is larger, 1/2 or 2/5? Well, 1/2 is 5/10, 2/5 is 4/10. So more inertia, less inertia. The object with less inertia wins the race because it's easier for that object to speed up. One more. So as I said, I'm going to spend a couple of, well, not 10 minutes maybe so. So to finish this topic and then the review. What's happening here is an object under influence of forces. Solid cylinder. What does it tell us immediately? This name tells us what coefficient should we use for calculating the moment of inertia. 1/2 mr squared relative to the axis, which is always the case. And so we can calculate this number. We know the mass, we know the radius, and the angular speed. Let's make it positive. 40 radians, that's the initial one per second. And it slows down by a factor of 3. So the final angular speed equals 1/3 of initial, okay. And it took 10 seconds to do that. So the magnitude of angular acceleration will be equal to, well, final angular velocity minus initial divided by time. And we know all these numbers. We know all of them. So we know this. That's the moment of inertia. And we know that. That's angular acceleration. And that's what we're looking for. The magnitude of that force which slows it down. What kind of a physical nature? I don't know, maybe we touch it with our hand, or maybe the friction is between the cylinder and the axis. We don't know. It doesn't matter. What we know is that if we apply the Newton's second law for rotational dynamics, we should write the magnitude of that torque should be equal to these two numbers multiplied. Well, that's it. And finally, this is a part of a review in a way, because a couple of students at least sent me an email asking to talk about this problem, but this problem is identical to this demonstration I wanted to do last time. So very quickly. Again, we have a system. It's a system. What's the difference between a system and an object? This is the difference, actually. Switching to the camera. Last time I'm going to use the camera. This is a wheel. It has a certain moment of inertia. If I pull on the string, you should have said that. Thank you. Oh, you saw it. Anyway, this is what you're looking at. My hand pulling on the string. Third time. So my hand is pulling on the string. Yeah. Only one object is a part of this consideration. This wheel, there is a force of tension acting on it, maybe the force of friction here. Of course, there is a kind of normal force which holds it. But relative to this axis of rotation, only possible friction, and this force responsible for the angular acceleration. Now, instead of pulling on the string, I'm attaching a weight, and that changes the situation completely, because now we have to use two body diagrams, one for this wheel and second for this weight. Well, not much to see, just that's it. Again, one object moving down, that's a linear motion, not rotational. So for this object, we have to write what law for the weight? What is the name for that law which we write for an object attached to a string? Someone should say something. Sure. What is the name? The name of the law for this object? Law of conservation of linear momentum? Yes, no? How many laws do we know, actually? Huh? Laws, not definitions. Newton's second law for translational linear motion, Newton's second law for rotational motion, the law of conservation of linear momentum, the law of conservation of mechanical energy, and kind of work kinetic energy theorem, which is basically the same law in disguise. So for this object, so this is the list of the laws should pop up in our head, and you should screen it and choose the one which you want to try. You're not sure if it's going to work, but so which do you want to try? First, second, third, fourth? For this object. for this one. Now, first one, yes. It doesn't, the weight doesn't rotate. It travels vertically. In this situation, straight down, no rotation, no collisions. Two forces acting on it, force of tension and force of gravity. Tension, gravity. So, positive direction. It starts moving down, that's velocity, and it's speeding up, that's acceleration, relative to this axis, using magnitudes. That's the law. Tension has a positive component, gravity has a negative component, and acceleration has a negative component. Done. But now there is a second object. Second object makes rotational motion. So for the second object, which law do you want to use now? Second law. Because now it's about torque and speeding up. So this is the direction of angular acceleration. It's speeding up, which means, angular velocity. It's speeding up, that means angular acceleration also clockwise. It wasn't the best choice. It would be much easier for us to look at the situation from behind of the screen. In that case, everything would have been positive. But it doesn't matter, of course. So what we should write is, now instead of mass, we should use the moment of inertia. Instead of acceleration, we should use angular acceleration. Relative to us, from this point of view, the component should be negative. Torque. Only one force acting, touching it, that's string. So the torque acting on this wheel is due to the string. It's clockwise. It's negative. But its magnitude is supposed to be equal to the tension times the lever arm. And for this situation, of course, the lever arm is just equal to the radius of this wheel. And because it's a disk, this is what we should write for moment of inertia of the disk. And linear acceleration and angular acceleration are related. Well, they're all related. Distance traveled is equal to the angle divided by the radius. Linear speed equal to angular divided by the radius. Linear acceleration, which we call tangential acceleration, equals to the angular divided by the radius. It's just only last expression is important at this point. So A equals alpha over R. And now the easiest way is getting rid of A and tension T. So, and of course, so what can we do? Well, multiply everything by -1. So M times alpha over R equals mg minus tension. And here, 1/2 the big M, the mass of the disk, times R squared times alpha. And I've divided everything by the radius. I want to get rid of this R. So now I have a tension at the top and at the bottom, plus and plus, minus tension, plus tension. They cancel each other out. And what's left is that expression we are looking for the angular acceleration. over R plus 1/2 oops. Have to make a correction. That's how they related. Sorry, alpha equals A times this, or A over this. So A equals alpha times R. Yeah. So -1 or big M times R times alpha equals mg. That's it. This answers the question. We just plug the numbers in and calculate for angular acceleration. If we know angular acceleration and everything starts from rest, we can calculate, for example, angular distance traveled over a certain time. Well, if you have the numbers, we just use this final expression to calculate whatever we want to calculate, because we just plug the numbers in. But the question is, what's going to change if friction now is acting? Friction always opposes velocity. So if the disk spins clockwise, the torque due to friction has to be counterclockwise. If the disk spins counterclockwise, the torque due to friction has to be clockwise. That's how friction works. So in this situation, if this weight travels down, the angular velocity is clockwise, which means torque here, provided by that friction between the disk and the axis, should be counterclockwise. So how does this change our equations? Friction doesn't act on this weight. That equation doesn't change. Friction acts only on this wheel. So we have to add one additional term to the Newton's second law for rotational dynamics. So again, in terms of our agreement, acceleration for this situation, angular acceleration is negative. Torque due to tension is negative, yeah, but friction provides a positive torque. So we should add this term. That's it. And done. So I've got several slides related to questions I've been asked about. And right now, before I go to those slides, please ask your live questions. Any questions first? Yes? I think there's been the slide about the situation. So, something like that, right? Let's measure everything from the bottom. So this is the initial height. Here, it travels through. In order to travel through the loop here, the normal force acting from the loop on this object has to be positive, or that the critical value, 0. Normal force, the magnitude of the normal force can't be less than 0 because magnitude is negative. So magnitude is never negative. So H critical means the normal force equals 0. That's the first statement that has to be made. The rest is a combination of two laws. The law of conservation of mechanical energy. If we neglect any friction, mechanical energy stays the same. So here, I'm answering the question, what's the difference between law of conservation of mechanical energy and work kinetic energy theorem? There is no difference. It's a matter of convenience. We use the law of conservation of mechanical energy if we know for sure there is no friction. In that case, kinetic initial plus potential initial has to be equal to kinetic final plus potential final. If friction is acting, we should add that term, the work done by friction. But as long as we said this word work, it's just easier to use work kinetic energy theorem, because kinetic energy final minus kinetic energy initial has to be equal to total work, the work done by friction plus all other works done by all other forces. And normally it's just easier to analyze each work step by step. But mathematically, they are absolutely equal to each other. So because here, no friction, I prefer writing the law of conservation of mechanical energy potential, okay. Initial so R mv initial squared divided by 2, and normally we set it to 0, plus mgh, that's what we're looking for, has to be equal to mv final squared divided by 2 plus mg, 2 times the radius of this loop. Now, people usually make a mistake here. They might assume that final speed is 0. No, it travels through. This is what is 0. Normal force acting at the top is 0, not the speed. The speed is not 0. The speed points to the left. That's the speed, what we call final, kind of, for this situation. However, at the highest point, if there is no normal force, only gravity is responsible for the centripetal acceleration. So now, Newton's second law also tells us that m times centripetal has to be equal to mg, or plus 0. M cancels, v squared over r equals g. This is this speed. So that's what we call the final one. So now we have two equations which we can solve mathematically. Questions, please. All right. At any time, you can raise your hand and ask a question. So, about two cars colliding, several students sent me an email. So I assume that the only reason for questions is not having a clear picture. This is about the law of conservation of linear momentum. But because these two objects travel perpendicularly to each other, the situation is two-dimensional. That's it. So we just have to consider that's the momentum number 1, which is equal to m1 times v1. That's the momentum number 2, which is equal to m2 times v2. But those are before the collisions. And we can calculate each momentum. Mass, speed, another mass, another speed. But what we should now write is the law of conservation of linear momentum, which says this arrow, which equals 1250 times 7, plus this arrow, which equals, actually I don't even read what kind of a direction. south and west. Well, I got kind of, okay. So you should, it doesn't matter. And that should be equal to 700 times 21. That should be equal to the final momentum of the system after the collision, because they couple and travel together. And that gives us the right angle triangle. We just have to remember that's the momentum, not the velocity. And this has to be equal to total mass of the system now times the new velocity of both. That's it. Now, another question was about the situation when a ball, for example, bounces off a wall. Again, we have to remember the difference between an arrow, a component, and a magnitude. So if this is the initial momentum, P initial, and after bouncing back, that's the final momentum. The change in the momentum, delta P, equals final momentum minus initial momentum. However, if we want to calculate the magnitude of that change, the magnitude of this change, this is what we should do. We should use magnitudes. So final momentum points to the right, so it's positive. But the initial momentum points to the left. So this minus doesn't go anywhere, it stays. It doesn't disappear. But what we have to subtract is a negative number. This, what we see inside the parentheses, represents the component of the initial momentum, which is negative. And minus minus makes it plus. So again, that's an illustration of the difference between a component and the magnitude, a vector and a number. Here, well, very briefly, what's happening here is a collision. That's the most important part. This ball, when travels down, no friction, yeah, we can apply the law of conservation of mechanical energy, m1 v1 squared over 2 plus m1 gh1 equals m1 v1 final squared over 2. So here at the bottom, this ball has a certain speed. That speed is final for the process of motion down, but that speed is initial for the next process, which we call collision. So what's happening? V1 and 0, that was at rest. And, well, that's before they collided. And after they travel, how would they travel? Well, of course, this one travels to the right. That one, we know, probably would bounce back. However, again, we also know that the actual motion depends on the ratio of masses. So to not confuse ourselves, let's just imagine that it still keeps traveling to the right. U1, U2. Because for this situation, we can apply two laws. Number one, m1 v1 equals, well, plus 0, equals m1 u1 plus m2 u2. And a second one, which we have derived, and we don't have to do it anymore. The second one is v1 plus u1 should be equal to u2 plus v2. Because we did that work once. We have proved that a combination of law of conservation of linear momentum and law of conservation of kinetic energy, which we apply for elastic collision. You see, it says leads to this equation. And now, well, this is 0. Yeah, it was at rest in, no, what was 0? Not, sorry. Not this is 0. This is U1. This is 0. V, letters V represent velocities before the collision. Letters U, both represent velocities after the collision. So the second ball was at rest. And now you can solve it. Pure math. Plug the numbers, you know masses, 2 equations, 2 unknowns. What I did to check if it works, I just used this expression to replace second unknown, U2, work it out, calculate U1, plugged it back, calculated U2. And it turns out, for my numbers, which I see on the screen, if you do this kind of calculation, U1 will be a negative number. What does it mean? It means that actually it points to the left. That's it. That's what it means. Here, place it here, distance number 1, distance number 2, and the magnitude of the forces acting on the third object must be equal to each other. So G MB times MC divided by R1 squared should be equal to G MA divided by MC R2 squared. This is the mass of the third object. And another expression we can write, the first R plus second R should be equal to the total distance between these two. And that's it. G cancels, this cancels, and the rest is pure math. Here, this is a problem I like, because it requires literal translation of the words we read into equations we write. Forces 1 and 2. So in both cases, those forces, well, have the same magnitude. And the magnitude of second, 5 times of the first. That's the very first equation we have to write. It has nothing to do to physics or any laws. It's what we're told by him. That's it. I mean the author. Now, we have 2 conditions to write. First condition is this torque, net torque, equals 0. How do we know? How do we know? We can read somewhere it was said. In each case, net torque equals 0. But if we have only 2 forces acting on an object, net torque equals 0 only if the first torque has the same magnitude as the second torque. They have opposite directions, of course. For example, relative to this axis, this torque is negative, this torque is positive. Relative to this axis, this torque is negative, this torque is positive. So they must cancel each other, which means they must have the same magnitudes. So case A, F1 times B must have the same magnitude as F2 times A. That's the axis. That's the line of action. This is the lever arm, B, for the first force. That's the axis. That's the line of action. That's the lever arm for the second force. So that's the first equation. That's the second. And now we can write the third equation. This is the axis. Doesn't have to be there, actually, but that's just natural choice. So this torque, that's the line of action. This is the lever arm. So this torque has magnitude of force times 1 meter minus A. It's a 1 meter squared. So this is 1 meter long. And that magnitude has to be equal to the magnitude due to the second torque. So That's the line of action. That should be the lever arm, F2 times B. That's all about what the lever arm is, what the torque is, and what the net torque is. Now we have three equations. The rest is not up to me, up to math. Here, I don't like this problem because of its wording. It really needs kind of, well, what can we do? I didn't write it. So first, let's see. The first question asks about this force. So the fastest way to answer, choose the axis at the feet. In this situation, we have only two torques. Negative due to force of gravity, positive due to arms. Now, this is the first tricky part. So we have to assume she's actually moving, but because it says constant speed, there is no acceleration. No acceleration means still everything, net torque, net force is equal to 0. So it's just to trick us. Still, torque, net force equals 0, and net torque equals 0. So relative to this axis, again, we have only two torques. They must cancel, which means they must have same magnitudes. So the magnitude of this force weight, so 50 kilograms times 9.8 times lever arm, which is 0.9, has to be equal to the magnitude of the opposite torque, which is that force she applies, times the lever arm, which is 1.5. Now, this is the force provided by both hands. The question is, what is the force provided by one hand? So what do? The force from one hand should be equal to a half of this number. That's it. That's another tricky part. So, and now we have to say that this is not a good picture, it's too small. It doesn't help us to answer the next question. The next question about muscles. So let's enlarge the picture. This is her palm. This is where she's touching the floor. And the lower arm is not strictly vertical. Yeah, there's some angle. Now here we have the elbow and the upper arm, so the shoulder. This is how it looks like. And the key word when we read it is the elbow. So we have to assume, they should have said it, but we have to assume that when they say the effective lever arm, it's relative to the elbow. So what's happening here? Well, this force points up, and this force due to triceps points at, how does it point? It points in such a way so the distance from the elbow to the line of action is equal to, well, that number where we have. So this is the effective lever arm. That's what they mean. Effective lever arm, yeah, 1.76 centimeters. And now the next number is here. So if we go down, this is 1.9 centimeters. So we just have to decipher what they mean because the wording is so unclear. But after doing that, the rest is simple. Again, everything is in equilibrium. So here, for the arm, as a single object, net torque relative to the elbow has to be equal to 0. Oh, actually, my picture So they should be opposite to each other. So actually, this arrow should point below, I think, like this. So it doesn't matter. It doesn't change the calculation. But from the physical point of view, one has to be positive, another has to be negative. Okay. And they must have exactly the same magnitude, which magnitude, what it is. This force from one hand times the lever arm should be equal to that force, well, let's call it tension in the muscle, times its lever arm. So we know this number, and we can solve it for this. So it's all in the picture. The last calculation is just if you know this number and you divide by her weight, that's a ratio. I don't know what it's about. Check in your 8th grade math or 6th grade math, I don't know. Two numbers, one divided by another. Okay, so this has been solved. This is the problem about the wheel and the weight attached to it. We just release the weight, it's speeding up, the wheel is spinning, that's it. This has been done. So if you want to calculate how many revolutions does it make, well, theta equals initial velocity times time, that's 0, plus acceleration times time squared divided by 2. That's the standard equation for the motion with constant acceleration, but now it's a angular acceleration. And acceleration has been found before. But if you use this equation, theta gives you radians. And, you need revolutions, so you have to convert radians into revolution. 1 revolution equals 2 pi radians, that's it. Done. That was my last slide. So please, any questions? We still have some time left, about 3-4 minutes. Yep, done. And everything is in there. So I'm going to post it. Not sure it's helpful, but movie might be helpful. Any questions? Yes? I don't know yet. Honestly, I'm thinking about it. Between 6 and 8. Yes? There is one student who didn't answer one of my questions. I'm not sure if that student is in the room. I'm just reminding them. I'm waiting for your response. Okay, no questions? We're done. Thank you. Again, this week lab will be held in a different room, 136.
Lecture on Friday, so I went to watch the lecture, and there's no sound for Friday lecture.
Okay. It happened before, that's why I use a backup, just in case. There is nothing to do about it.
Okay.
I will send an email. You should send an email to me. I will send an email to IT people. Okay. Maybe it's somewhere and they can put it back. There is another way. I also, as a backup, upload those lectures to YouTube. Okay. That might have sound. It might not see it the same way from a different perspective, but it might have sound.
Okay.
So you should check.
Okay.
Okay.
Thank you. Good day. Was there a sign-in sheet?
No. Yes. I sent you an email. sent you an email and I said, I offering you to take an exam a different time. Yes, and it was last week. If it was you, because student sent me an email last week, and I said, take an exam from start to finish. So it wasn't you. It means there's another student who sent me the schedule, and that student has a window. Which windows do you have? I don't know. That's not the way it works. I need your email with all the information, with your schedule. So in that case, I can think about it and give you some options.
Actually,
Yes.
Okay, Doc.
No, you said there's no sign.
No. Well, depends. Yes. No, I don't know. It depends. What do you call the apparent weight? Yes. And that, well, so the apparent weight is not the normal force. It's the force which is added to it, but it has exactly the same magnitude. So, if you solve this equation with normal force, that number tells you the apparent weight.
Yeah. It was a part
Well,
3
this
or part
equation
4 that had all of the like satellite
is wrong.
equations and stuff.
I think it's part 4.
Part 4, yeah. I want to ask him.
I don't know. How do you know with plus and minus? You don't have any vectors, you don't have any forces. You need to draw a free-body diagram. Then we can check. Okay. Now it works. Now it is correct. Exactly. Now it is correct.
but as normal force, I
What?
can solve for normal.
You solve for normal force. Yes. Yes. Yes, I'm listening.
Okay, I'm still confused about the difference between the hollow cylinder and the solid stuff.
The difference is, well, one is hollow, another is solid.
Yep, meaning you said the
Meaning-
mass should be different.
No.
No.
I said that
You can have the same mass.
they can have the same mass and they can have the same size, but in that case, I said they will have different moment of inertia,
So
different by a half. That variable we call I, capital I,
yes,
that will be different for them.
yes. So which one is which one? Which one is which one? The inertia. Which? Sorry.
Yeah, that's capital I. That's what we call inertia, rotational inertia, or moment of inertia. That variable is equal to mass times radius squared for the whole cylinder.
Okay.
But it will be equal to
Half.
1/2
For the hollow.
times mass for the whole, for the solid one.
For the solid.
Yeah, which has no space in it.
Oh, okay. So 1.5 for the solid one, and
Yes.
Is that on the equation sheet, or is that something we just need to know?
You should know by now.
Oh, yeah.
But it is on the equation sheet. That's good. Yeah, now, yeah.
For the part 4 of the homework too, asks a lot of the orbital questions with satellites and stuff using scientific notation. Are there going to be a lot of questions like that on the exam? And if so, do you want us to write it using E or just like with the exponent? Like, do you want us to do 10 times?
What do you mean?
Like for
You don't have.
like for the gravitational.
You don't
constant.
have to use scientific notation or any other special
Thank God.
notation.
That's
You
all I
just,
wanted to ask.
you know, It's a number. It has to be correct. How do you write it? It's up to you.
Okay, thank you.
I just have another question.
Yes.
So for the part 5 or homework 2, I only submitted a couple questions for a couple times, but I guess it's because of some internet problems. I only have like one last chance for all my questions left for the whole problem set. So
That's, how could that happen?
I don't know.
Send me an email.
Okay.
I can give
For
you.
what information do
extra-
you need? What information do you need in the email?
Everything you just said.
Okay. Thanks. Sorry about that.
No problem.